Assalamu alaikum and good morning, everyone. Welcome to the 59th Distinguished Lecture Series organized by the Faculty of Engineering, University Technology, Malaysia. My name is Nick Runzi and I'm the head of the Power Electronics and Drives Research Group, School of Electrical Engineering, UTM. Today, we are very fortunate to have our guest speaker streaming live from South Korea, Professor Kyo-Beum Lee from Ajou University. The title of his talk for today is going to be Reliability of Capacitor in Power Conversion System. Prof. Kyo is not new to us. I met Prof. Kyo when he and his students visited our lab in UTM a few years ago. And Prof. Kyo is also a regular participant to our biannual conference organized by UTM and the IEEE Malaysia since 2014. In fact, we have invited him to give a keynote speech at the 4th SENCON, which was held in Jakarta in 2019 last year. So today we are very, very happy to meet him again in cyberspace. And without further ado, I would like now pass the session to our Dean, Professor Rafiq, to introduce Professor Kyo. Over to you, sir.
Thank you, Professor Nick Rumzi, for chairing the session. Assalamualaikum warahmatullahi wabarakatuh. Hello, welcome everyone. Welcome to our 59th UTM Engineering Distinguished Lecture Series. My name is Muhammad Rafiq and I am the Dean of Engineering, University Technology, Malaysia. Today, it is my utmost pleasure to welcome Professor Kyo-Beum Lee from Ajou University, South Korea. A bit about our distinguished speaker today. Kyo-Beum Lee received the BS and MS degrees in Electrical and Electronic Engineering from Ajou University, Suwon, South Korea in 1997 and 1999 respectively. He received a Ph.D. degree in Electrical Engineering from Korea University, Seoul, South Korea in 2003. From 2003 to 2006, he was with the Institute of Energy Technology at Aalborg University, Denmark. From 2006 to 2007, he was with the Division of Electronics and Information Engineering, Chonbuk National University, Jeonju, South Korea. In 2007, he joined the Department of Electrical and Computer Engineering, Ajou University. Professor Lee's research interests include electric machine drives, renewable power generation, and electric vehicle applications. He is an associate editor of the IEEE Transactions on Power Electronics, the IEEE Transactions on Industrial Electronics, the Journal of Power Electronics, and the Journal of Electrical Engineering and Technology. So that is a brief biography of our distinguished speaker today. Here now is Professor Kyo-Beum Lee from Ajou University, South Korea, to talk about reliability of capacitors in power conversion system. Professor Kyo-Beum Lee, over to you.
Okay, thank you. Let's start. Thank you. And then let's start my presentation today. I am Kyo-Beum Lee from Ajou University. And then it's not easy to pronounce my name. So my friend just call me Kyo, and then you can call me Kyo. And then today I will talk about some reliability of capacitor in power conversion system. In this lecture, I will cover the introductory information on reliability, capacitors, and some researches about reliability improvement of capacitors. Okay, let's start. And then this is content of my lecture. First, I start the introduction of my laboratory, and then I will show you some reliability of power conversion system and the characteristic of capacitors. After then, I will talk about the reliability of capacitor. And finally, I will show you some various studies to improve the reliability of capacitors briefly. It's okay. And then, this is my laboratory. I'm the advisor of the Power Electronics Lab in Ajou University. We have 29 students, not a student, 29 persons in my laboratory, and then one assistant professor. He's from UTM, Ibrahim, and then one research professor, and then 3 PhD student, and also 20 master student. And then my research area is are some electric vehicles, motor drives, reliability, renewable energy system. It depends on some research project. Some government wants some support some project about some electric vehicle or a charger. So we will do that. There are one laboratory and then 2 offices for researchers. One laboratory inside the university title is Power Electronics Lab, and then there are 2 offices outside of university. One is Green Energy Lab, near the university, and the second office is Power Conversion R&D Centers, outside the university, far from not far from, just 15 minutes by walk from the university. These are the papers for 3 years. We have just the 70 international papers, and then 43 some conference paper. From 2020, because of COVID-19, and I couldn't attend some conference in abroad. So I cannot make sure some research result about some international conference paper in the future. Anyway, this is some interesting slide. I start to attend some conference at Seoul from 2014. These photos, and then I also attended some PCON in the last year, Jogja in Indonesia. I spent a great time at the Jogja in Indonesia, and then I received some paper award in the PCON 2016. It was a great experiences in my life, and then I really hope to attend some next year SENCON in Joburg again. And then I would like to meet my friend Nick in the next year. Okay, let's start my presentation. First is, what is reliability? It's very important, and then I will talk about the definition of reliability, necessity of reliability research, and classification of reliability research, and the reliability of power conversion system. Okay, what I'm going to do in this slide, what is reliability? Okay, the reliability in a power conversion system is defined as follows: the probability that an item will perform or require the function without failure under state condition for a state period of time. Okay, that's the reliability in a power conversion system, or some available lifetime of system. In short, the probability of system failure, or knowing the time when it will fail. If we can know whether the system will fail, we can prevent various accidents by repairing the system in advance. And then this figure, this below figure shows a failure rate of the power electronic system. Let's just look at the trend. Okay, first, only failure is mainly caused by user mistake. So the left side of this figure. First, only failure is mainly caused by user mistake. So the failure rate is relatively high at the beginning of the system operation. The next, the middle part of this figure, next is unpredictable failure or trouble. Even in the normal operation, the probability of failure is not completely zero. You know that. So some degree of possibility of the failure should be considered in the middle part. The last is wear-out failure. You can see that the failure rate increased due to wear-out. Wear-out failure will be covered in detail later in this presentation. Okay. This shows why reliability research is necessary. Okay. The power system is composed of various components such as a generation station, transmission line, and transformer and power conversion system. Among these components, the failure rate of the power conversion system occupies a large proportion. For example, wow, how can I pinpoint? For example, in a PV system, the failure rate of power conversion system reaches around 37%. Therefore, to improve the reliability of the power system, it's essential to improve the reliability of the power conversion system. This figure, below figure, is the classification of reliability research field. All the classified research fields are being actively researched now. Okay, and then next slide. Okay, oh, sorry. Next slide, that's the slide number 9. Okay, in this slide, I talk about the power conversion system. The power conversion system is composed with the various devices. It can be divided: source, power electronic circuit, controller, and the load. The more than 50% of all the power conversion system is caused by the capacitor and the power device in power electronic circuit. Among these two main causes, capacitor failure is dominant. The main stressor induced to failure of devices is thermal stress. You can see some table. At the below the left, stress or power conversion system components are shown in the table. But you can see some references. You can find some more in detail in the references. Okay. Okay, from this slide, in the second chapter, I will talk about capacitor. As I told you before, capacitor is the most frequently broken devices among power conversion system component. Therefore, I told you before, some with power device around 40%. Yes. Therefore, we will focus on capacitors. I will explain the type and the characteristics of capacitor in power electronics system. As you know, I will analyze in power electronic system rather than analyze on the chemical properties of capacitor. It's okay? This is the structure of aluminum electrolytic capacitor. You can see some sandwich, like a sandwich. Aluminum electrolytic capacitor is composed with aluminum and the electrolyte solution and the oxide film, as shown in this figure here. The main factor of capacitor is capacitance. Capacitance are okay. This, and then Lipper current rating and volumetric efficiency. In power conversion devices, capacitors should be selected. Consider these main factors. The main factors: capacitance, Lipper current rating, volumetric efficiency. There are various kinds of capacitors. I will talk about later the characteristics of each capacitor from this slide. Next slide. Okay. the type of capacitor can be classified as follows. We can classify into fixed type and variable types. Among them, fixed type capacitors such as ceramic, film, and electrolytic capacitor are widely used. So in this presentation, I will focus on these fixed type capacitors. The ceramic capacitors have no polarity, and the materials with high dielectric constants such as barium titanate is used as dielectrics. Because of its high frequency characteristics, it is widely used for noise removal. And then the second, film capacitors also have no polarity. Polypropylene is used as dielectrics. Electrolytic capacitors use a thin oxide film and aluminum as a dielectric and an electrolyte. The dielectric inside the electrolytic capacitor can be made thin. So the important thing is the capacity, the volume ratio of electrolytic capacitor is very large. So that's why the electrolytic capacitor used in many application areas. Okay, electrolytic capacitors have polarity and outstanding low frequency characteristics, so it's widely used for rectifier and the low frequency bypass. Also, there are various types of capacitors such as titanium capacitors, mylar capacitors, and so on. Many related materials are on the internet and in the books, so it's recommended to study further outside beliefs of them beyond this presentation. But I told before I will focus on some fixed type capacitors such as ceramic, film, electrolytic capacitor. Okay, in fact, when designing a capacitor, we have to consider number of factors. I told before about the main factor in the slide 11, no, 11 or I think, 11, okay, that's correct. Capacitance, ripple current rating, volumetric efficiency. It must be designed by comprehensive considering various factors such as voltage rating, capacitance, stability, ripple current rating, temperature, and ESR. ESR is equivalent to series resistance. Okay. Also, it's very important to consider volumetric efficiency, lifetime, and the cost for improved system power density, reliability, and cost competitiveness after the capacitor specification is designed. Okay. Okay. Let's talk about how we can use capacitors in power electronic system. These are two examples: motor drive system and the photovoltaic system. We use the capacitor in the motor drive system as an EMC filter, DC link, and DC source, and the alpha filter for inverter system. In the case of photovoltaic system, we also use various ways as EMC filters, DC links, and filters. In other words, a capacitor is a device that plays an important role in power electronic system. Okay. And then I will continue to focus on a capacitor used in DC link. Okay. Okay, this slide. I will talk about some characteristics of capacitors for this link. Okay, we mainly use film capacitor, ceramic capacitor, and the electrolytic capacitor as a DC link. This figure shows the comparison of various characteristics of each type capacitor. Film capacitors have long lifetime, excellent ESR, equivalent to series resistance characteristics, and high allowable ripple current and voltage rating. Okay, but they are bulky and vulnerable to high temperatures. Yes. And then ceramic capacitors are relatively small in volume and withstand high temperatures compared with film capacitors, but they are expensive. Electrolytic capacitor is one of the capacitors which are very popular for this link because of its low price, small volume. But the ESR is relatively large, allowable ripple current is small, and the lifetime is short because of the possibility of electrolyte vaporization. Okay, but one of the important thing is electrolytic capacitor, outstanding energy density, low cost. It's okay. Okay, in the previous chapters, chapter 2, I talked about the basic knowledge of capacitors through a simple structure, factors to consider when we use capacitors, and various applications in power electronic systems. In this chapter, we will learn about the reliability of capacitors. First, the failure mode, the failure mechanism will be examined according to each failure mode and stressors, and we will conduct more detailed analysis of each failure mode. After that, I will explain the reliable design process of this link in power conversion system. Okay, I have to pump up speed. We are now slide 17. Look at this failure mode. There are failure mechanism and critical stressor according to the type of capacitor. AR cap stands for electrolytic, and then MPPF stands for film, and then MLCC stands for ceramic capacitor. First, there are 3 types of capacitor failure, such as short circuit, open circuit, and wear-out failure. All these type of capacitor are dominant in wear-out failure. Also, in case of AL or MPPF cap, the open circuit failure is dominant, and the short circuit failure is dominant in MLCC capacitor. Temperature and voltage are common stressor for each type of capacitor. And then by the type of capacitor, AL cap is vulnerable to the current stress. MPPF cap is humid, and then MLCC cap is vulnerable to mechanical stress. Okay. As for the self-healing capability, MPPF cap is the best, MLCC cap is the worst. Self-healing here refers to automatically recovering insulation properties by scattering deposited metal when an accident occurs due to internal or external causes. Self-healing prevent secondary accident of capacitors. To prevent the spread of accident, we will focus on AL capacitor, electrolytic capacitor with the shortest life among the capacitor. I told you before, low cost is also one of the reasons we will focus on the electrolytic capacitor. Okay. I told you before, some electrolytic capacitor has high ESR and the low permissible current ripple. When a large ripple current is applied on the electrolytic capacitor, a high electrical loss occurs due to high ESR, which causes heating inside the capacitor. The increased heat makes electrolyte to vaporize faster, which accelerate the wear-out failure of the capacitor. Okay. 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 Next, let's talk a closer look at the three failure mode that can occur in electrolytic capacitor. In fact, short circuit failure is not a dominant failure mode. This failure mode is mainly caused by a defect in the capacitor itself. In the case of open circuit failure, it can also be caused by manufacturing defect and also occurs during an unstable control. The above two failures, short circuit, open circuit failure mode, can be considered as an uncontrollable failure. And it means that we cannot control or we cannot manage these two failures. So we focus on wear-out failure. It's caused by unstable or unsuitable control and high temperature and humidity. We can control the operating environment to delay the time of failure or predict the lifetime. Okay. The table, or below table in this slide, shows electric capacitors, the dominant failure mode, mechanism, and the stressors. Okay. Okay, look at this causes. These causes of electric capacitor short circuit failure. In the AR-cap, electric capacitor short circuit failure occurs due to the dielectric breakdown of separator and the breakdown of the oxide layer. In the case of insulation breakdown in electric cell, it can be caused by the use of a separator containing impurities or an excessively thin electrolytic cell. In the case of destruction in oxide layer, it can also caused by partially deficiency of oxidation or excessive charging and discharging. Anyway, sorry, main cause of the short circuit failure is manufacturing defect. Okay. The open circuit failure of electrolytic capacitor is caused by poor terminal connection and structural destruction. These are mainly caused by mechanical stress. Another cause is the collapse of oxide layer, which can be caused by excessive charging and discharging. The last cause is a decrease in the foil capacitance on the anode side. This is caused by an excessively high upright voltage. The waveform of the figures on the right show before and after capacitor open circuit failure of modular multi-level converter system. The MMC is usually used for high voltage DC and medium voltage DC power converter system. Okay. This slide, the open circuit failure of electrolytic capacitor is caused by a poor terminal connection. Oh, no. Okay, page 22. Okay. This is the wear-out failure of capacitors, electrolytic capacitors. The capacitor wear-out failure can be caused by evaporation of the electrolyte. The core temperature of capacitor increases due to the component of current following through the capacitor, which causes the electrolyte to evaporate. The next cause is a decrease in positive and negative foil capacitance. The positive foil is reduced by an excessively large applied voltage, and the negative foil is reduced by applying a negative voltage, which does not match the polarity of the electrolytic capacitors. Where's the last? Okay. The last causes is high ambient temperature and humidity. The wear-out failure is mainly caused by the operating environment, and the cause is an increase in capacitors and ESR in general. The lifetime prediction of capacitor is to predict the time of wear-out, not short circuit or open circuit failure. Okay? The short circuit and open circuit failure mainly caused by manufacturing defects. So we would like to focus some wear-out failure from this slide. Okay, this is a criterion to judge the wear-out failure of the capacitors. In the case of electric capacitor, if the capacitor decreases by 20% or ESR increases by 2 times, we can judge a wear-out failure. The degradation indicator are capacitance or ESR or both. In the case of MPPF cap, we can judge its failure when the capacitance decreases by 20% or the dissipation factor increases 3 times. We can use mainly capacitance as an indicator. MLCC capacitor are judged as failure when their capacitance decreases by 10%. Insulation resistance is less than 10 mega ohm, or the dissipation factor doubles. Capacitance and insulation resistance are used as an indicator. From this criteria, the wear-out rate of the capacitor increases rapidly, drastically. Okay, so we can judge this failure criteria. Okay. The next slide. This is a reliable design procedure for DC-link in power conversion system. The first step is a high-level definition. This is the step to consider the topology, control method, and design limitations of integral devices. It's very usual in the power electronics engineers. The next step is the DC-link level definition. It's also in this step, the capacity of capacitor is calculated considering the factors such as voltage level of the DC stage and the limit of the voltage ripple component. Next is the decision of capacitor type. We should choose most suitable capacitor type based on several factors that I told before. The fourth step is electrical analysis and design. In this step, we can determine to configure a capacitor bank and take into account parameter changes and operation according to electrical analysis. The fifth step is thermal analysis and design. We have to consider the capacitor temperature estimation, and the cooling method. The sixth step is reliability analysis and design. In this step, we conduct the analysis of failure mechanism and lifetime prediction. Final step is robotics analysis and optimization. Comprehensive evaluation and optimization of the reliability, robotics, cost, size, and design margin of DC solutions. Okay. Okay. This is the last chapter. In the previous chapter, I talked the need for reliability research based on knowledge of capacitor and reliability. In this chapter, I would like to say about some studies to improve the reliability of capacitor. There are 4 categories: lifetime prediction, capacitor minimization, and the conditioning monitoring, and the lifetime extension method. Okay. The first is lifetime prediction. As analyzed in previous slide, the lifetime prediction of capacitor is to predict time when the wear-out failure of the capacitor occurs. The first step to lifetime prediction is electrothermal analysis. I told you before, the liquid current flowing into the capacitor causes a loss due to ESR, and this loss increases the internal temperature of the capacitor. In this slide, I'm now talking about the process of temperature calculation. We can calculate the power loss due to ESR by considering the current flowing through the capacitor. After then, we can estimate the core temperature of the capacitor by using thermal modeling that is calculated by using the power loss. Okay, and then by using power loss, we can calculate. Oh, sorry. This is analysis of the nonlinear damage accumulated on the capacitor. The first equation is the lifetime modeling. We can calculate the lifetime of the capacitor using the core temperature obtained in the electrothermal analysis step. The typical process of capacitor life prediction, and at this stage, but recently, several methods have been introduced to predict accurately the lifetime of capacitor. One of them is nonlinear damage accumulation analysis. This is the second part. The nonlinear damage is modeled through a complex equation. We can recalculate more accurate core temperature based on new model. Okay, the last is Monte Carlo simulation and prediction of lifetime. In this step, we applied the temperature considering newly calculated nonlinear damage to the life model and the statistical techniques for various parameters. This process allows more precise prediction of capacitor lifetime. Okay, in this slide, I will talk about minimization of DC capacitor. There are many research results about capacitor minimization for quite a long time. The purpose of minimization of DC capacitors is to apply high reliability capacitors such as the thin or film capacitors first. The minimization of DC capacitor is largely divided into 3 categories. There are performance trade-off, passive, and active method. Among them, various methods have been studied for passive and active minimization method. Let's check simple concept of passive and active approach. Passive minimization method is basically an approach to reduce the size of DC capacitor by using an additional passive filter. This approach can be implemented simply by adding additional passive component, but compared to other approaches, it has advantages of increasing the size and the weight of the system. Active minimization method is an approach to minimize liquid component power by connecting active circuit to series of parallel. the overall control becomes complicated because an additional control algorithm is required for the active device. Related studies often target the small capacitor system, such as LED drive. This is condition monitoring. Condition monitoring is a method to improve the capacitor reliability by determining the degree of aging. Condition monitoring methods are largely classified into two types, online, offline. The online condition monitoring monitor the state of the capacitor during power conversion system operation, whereas offline monitoring technique monitors the condition when the PC's power converter system stop operating. The state of capacitor is determined by observing indicators such as ESR, capacitance, ripple voltage, volume, and temperature. Typical degradation indicator for condition monitoring include ESR, capacitance, ripple voltage, volume, and temperature. Among these degradation indicators, ESR and capacitance are the most widely used for condition monitoring. They are more than 90%. Okay. These are variable condition monitoring techniques, and then okay. There are three representative approaches. Three representative method are capacitor ripple current sensor-based method, circuit model-based method, and data and advanced algorithm-based method. There are three methods. The first is capacitor ripple current sensor-based method. It directly measures the ripple current of a capacitor through a sensor and analyze them to calculate ESR or capacitor. This method is largely classified into two types, depending on the injection of the additional signals. Without injection of an additional signal, we can calculate the ESR by directly measuring the capacitor ripple current, but this is not a common method. In the case of condition monitoring technique with injection of an additional signal, a sine wave voltage with a specific frequency band is injected into the capacitor, and the resulting current is analyzed to determine the condition of capacitor. This is the circuit model-based method. This technique is also classified according to whether additional signal is injected. For a technique that do not inject additional signal, the ESR or capacitance is calculated based on the principal operation of the PWM converter. Capacitor current is directly estimated using the sensor values in the existing power conversion system. This method is the best method theoretically, but it requires the precise sensors. Also, when the topology becomes complex, its analysis is very difficult. The following is the circuit model-based method that inject additional signal. This is a method of injecting the sine wave current with a frequency lower than the line frequency and analyzing the voltage of the capacitor induced by current. It's known that the online condition monitoring is possible. Below is an example of ESR and capacitance estimation using a circuit model-based method. Okay, the last is data and advanced algorithm-based method. Recently, research on applying the AI, artificial intelligence technology, is to power electronics is actively being conducted. In the reliability research, some studies were conducted to estimate the state of capacitor using neural net. The advantages of this technique is that it estimates the condition of capacitor using only the input and output regardless of the internal operation of the power converter system. Input are composed of values normally censored in PCS control, and the output are capacitance or ESR through the neural network. We can estimate the relationship between parameters through data training. We don't need an additional circuit or signal injection, but we need high quality data to train this neural network system. That's very important point for AI application. You have to know that. According to research results, the estimation results are very accurate with high good and many good quality data. Okay, without good quality data, we cannot make accurate research result, accurate estimate value. Next is lifetime expansion of capacitor. In my laboratory, we are now focusing on these studies in various ways. Each, in my opinion, easy approaches from the power electronics area to make system reliability. This is a method to improve reliability by reducing the current stress of the capacitor to delay the wear-out point. Okay. Let's take a close look. The target topologies is a 3-level inverter shown in the below figure. The first, I will explain the neutral voltage. Neutral voltage is the point between DC capacitor connected in series, and it enables the inverter to make 3-level output voltage. As shown in this figure, you can see that the current of the upper and lower capacitors are combined into the neutral point. Neutral point current and the DC current are directly related and then have the relationship as this equation. In other words, it's possible to reduce the current stress of DC capacitor by reducing the neutral point current. When the state of A phase is O state, the current of that phase flow to the neutral point. Okay. First, I have to finish up my presentation. Please wait a second. I will level within 5 minutes. First, let's analyze the neutral point current and then the conventional PWM strategy widely used in reliable inverter systems, CVPWM, and then the carriage-based PWM, and then the light figure, we can see some generate voltage vector. When the reference voltage vector locates A section, the output current corresponding to the 1I section in the lower left figure, we can see the neutral point current and the pole voltage in the light below figure, lower figure. By using, we can skip. This is conventional PWM strategy for a 3-level inverter system. So in order to reduce neutral point current, we had to avoid to use POO and ONN. You can see, this POO and then ONN. This switching vector causes a large current ripple. It's okay? And then by using proposed algorithm, we can reduce this neutral point current. But we have to avoid the use of POO, ONN. In the proposed method, neutral point current is reduced by using PON and ONO vector instead of POON or ONN vector respectively. When the switching state is PON and ONO, B-phase current flow into neutral point, thus the magnitude of neutral point current decreases, like this figure. Okay? Okay. This is the effect of reduced leakage current with the proposed algorithm. Okay. The common mode voltage variation range we can reduce by the proposed algorithm. And then this is evaluation. Experiments were conducted 10 kilowatt T-type inverter system before applying the proposed method. RMS value of neutral point current to 2.85 ampere. After applying the proposed method, the RMS value of neutral point current is 2.0 ampere. We can reduce around 27%. We can also see the variation range of common mode voltage is reduced significantly. Okay. Summary. Okay. I introduced the necessity of studying reliability of a PCS, power conversion system, then focusing on capacitor, which has dominant role of PCS fault. We found out the characteristic and kind of capacitor. And we analyzed the mechanism of capacitor fault and then checked the design process for reliability of this link. And then finally, I introduced a few studies for increasing capacitor reliability. This is the references. These are references. And then it's a book, the first reference. And then you can download the website. Okay, this is a book for 2017. In the 2017, it's okay, very interesting book. And then capacitor is one of the hot topic in power conversion system reliability, along with power semiconductor. I think from 2020, the research topic in power electronics, there are only two trends. One is modularity, and the second is reliability. I mainly explained the introductory content because the range of reliability research is too large to deal with in one lecture. But if you want to study more about reliability, I recommend to refer the references or some book. And finally, I finished the lecture expecting that all you guys grow up specialists in the future. And thank you. Oh. Okay. This is the end of my presentation. No? Okay. Are there any comments and questions? Electric train along the line power is supplied in loop. As train moves from the loop to loop, in between the loop power capacitor supplying the power, what is the common type of capacitor used in electric train? What is the common failure mode for the train capacitor? And what method can be adopted to increase the reliability of the capacitor? Okay, there are three questions. In No, first question we can choose. I told you it's my presentation, and then our first step. Oh, wait a second. Research, and then capacitor. There are the fixed capacitor and then variable capacitor. We can choose. Oh, where is the question? Okay. Train moves to right, and then capacitor supply. Okay. The common type of capacitor used in electric train, and then I cannot make sure some train we can use a filling capacitor, or sometimes we can use ceramic or electric capacitor, but it depends on application area. What's the common value more for the train capacitor, and then what method can be adopted to increase the reliability of the capacitor? I told in this slide there are so many ways to increase the reliability of the capacitor. So I cannot make sure some exact method, but you can find some way. The easiest approach way is from the power electronics area is reduce the current ripple to flowing into the capacitor. That's the easiest way to improve the reliability of power electronic system.
Yeah, Prof. Kyo, sorry about the technical problem just now.
Yes,
sorry about the technical problem just now. Okay.
Finished?
There is another question here. It's also from the same person, Muhammad Afifi there. In another application, capacitor is to supply power to elevators in case of blackout. What type of capacitor is most suitable for elevators? I think he's talking about supercapacitor or something like that. Yeah.
Yes, but I cannot make sure, but some is depend on some spec. Yes, but volume and then the cost.
Yeah.
Yes, but
I think it is more of a supercapacitor or ultra capacitor, I think.
Yes.
Can I ask you a question, Prof. Kyo?
Yes.
It's about the now people are talking about the wide bandgap devices, silicon carbide, and the gallium nitride and so on. And how is this, because they have a higher switching capabilities and higher blocking voltage block. So how this affect to the usage of the capacitor in this power conversion with these new devices, the wide bandgap? What do you think, your comment on this?
But reducing the capacitor means some application area we use some electric capacitor, and then we would like to change some filling capacitor. We can reduce the volume. It's one of the direction to reduce the capacitance, and then we can reduce we can improve the density of power electronic system. And then home application area, some the aircon or some other application area, the most of company want to reduce the capacitor because of the dominant in the failure, the power electronic system. But what's
the question?
Yes.
The wide bandgap devices, the silicon carbide and the gallium nitride. How is this affect the the capacitor in terms of the voltage, current, ripple, and so on?
Carbide and the gallium nitride switching device, we can make some faster switching, and then we can reduce the volume of the power electronic system. I mean, also we can reduce the size of capacitor or some inductors. But one of the important thing is that the switching device, we have to make some strong protection scheme for the switching device. The main research trend of the switching device is filter design and capacitor inductor design. And the more important thing is some gate driver for the switching device. But some to make some gate drive, we had to consider some protect, but it's not easy. I adapted some gate drive. I bought some gate drive from the main company, but I tried to make our own gate drive system. Is not easy to protect a circuit, but that's the main important point of that switching devices.
Yeah. All right. So I think we have go past the time limit that we have for 1 hour now. So I think we have to stop the session now. Normally, our dean, Prof. Rafiq, will give a he's on the air right now. So I will pass the session back to him then. All right.
Prof. Rumzi, thank you so much for sharing the session and moderating the question and answer. We had one from Prof. Afifi there. And to our distinguished speaker today, Professor Kyo-Beum Lee, thank you so very much for accepting our invitation to speak at UTM Engineering Distinguished Lecture Series. And to all of the viewers worldwide, thank you for watching the Distinguished Lecture Series. We have, do stay tuned because we have many more lectures for you. Until then, bye-bye for now. Bye-bye, everyone.
Okay.
Bye.
Thank you. Terima kasih. Bye.
Yeah, see you soon.